Hello, my name's Bill VanDoren. I work in the Bureau of Forest Fire Control and Forestry as a forest biometrician, which means I work with measurements, data, models, and predictions around forests and their management and ecology. I'm very grateful for the opportunity to speak with you this evening. During my brief time today, I'd like to accomplish several things. First, I'll provide a short overview of the Continuous Forest Inventory, or CFI program. Simply put, CFI is one of the most important tools to help us know what we know and learn what we can about the forests the Bureau stewards at a strategic level. I'll provide some examples of very general questions it's helped to answer in the past. I'll work through an example of estimating carbon stocks and components of change as an example of how the CFI program addresses questions on forest ecosystem carbon dynamics. And finally, I'll describe how our CFI data can help explore the relationship between resiliency and climate change adaptation and forest carbon. The CFI program is one of the best tools the Division of State Parks and Recreation has to help understand both the potential of the forests it manages to mitigate atmospheric carbon, as well as their adaptive capacity and response with respect to climate change. Our CFI program is very similar to the United States Forest Service's nationwide Forest Inventory and Analysis program, in that it inventories and samples the lands and vegetation managed by the division. Our CFI program operates at a strategic level, meaning it gives us high-level information on the status and trends of forests. It complements operational inventories we conduct before and after forest management projects. Measurements and data collected through the CFI program help generate reports on the current character and condition of forests and how they're changing. They're used in modeling individual tree characteristics and stand dynamics, and are used to model forest growth and yield into the future to evaluate trade-offs between different management approaches. At the beginning of each calendar year, we identify locations that are scheduled to be remeasured and identify new acquisitions and determine if new sample plots need to be established. Our team then visits the sample locations and plots to see if they're on property, and if so, measure trees, vegetation, and other forest attributes. We then review and compile the collected data. The Management Forestry Program and its predecessors have conducted strategic inventories of the lands it's managed since the 1920s and 30s. While it's evolved over time, the CFI program as it currently exists was established in the late 1950s. Approximately 1,100 plots were established then, and 6 decades later, we're now measuring those original plots a sixth time. As the land base has grown, so has the number of plots, to the point where there are now over 2,000 plots with measurements on over 100,000 trees. Of course, none of this would be possible without the dedication and expertise of my colleagues in the Management Forestry Program, licensed professional foresters and other professionals in the field collecting these measurements. This, and the Division of Water Supply Protection's CFI programs, are some of the longest continually operating permanent sample plot inventories in the country. So, our current program owes a huge debt of gratitude to our predecessors for their forethought. Over the last measurement cycle, we relied on a team of 9 licensed professional foresters that are year-round employees, and 5 seasonal employees devoting variable amounts of time to CFI. There had been 3 seasonal employees dedicated to CFI as well over the past 7 or 8 or so years. Late last year, through the DCR's Strategic Readiness Initiative, one of those 3 seasonal positions was converted to a year-round position, helping to gain some stability and efficiency in the CFI program. This map shows the distribution of CFI plots on the properties the division stewards across Massachusetts. As we look at this map, I want to point out first that the CFI system I'm discussing today was established by the Department of Natural Resources. After successor agencies merged to form the DCR, we've been gradually including properties like Blue Hills, Middlesex Fells, and Breakheart reservations that were managed by the MDC. Second, the Division of Water Supply Protection operates its own similar but independent CFI program tailored to its mission. It also has a long, rich history, with the first 360 plots being established around the same time, 1960, at the Quabbin, with 8 remeasurements between then and now, and close to 600 total plots across all 4 watersheds. Our field measurement protocol has varied slightly over the years. Here's a diagram of our current plot design. The inventory was initially commodity-focused, but has since grown to include measurements and observations of the greater forested ecosystem in a holistic fashion. We currently sample over 200 attributes, including site and stand characteristics, the dimensions, characteristics, vigor, and fate of live, standing dead, and down dead trees, characteristics of other vegetation, including vines, shrubs, herbs, forbs, ferns, grasses, and invasive plant species, downwoody material of all size classes, and forest floor characteristics, including the litter and duff. So what can we do with all the data we collect? Well, we get asked questions, a lot of questions, about the land we steward, both from our staff and the public. The CFI data can help us answer questions about conditions at a particular point in time. Here are some examples of estimates I've been asked to provide relying on our CFI data, and I'll highlight just a few of them. For example, we can estimate that, at present, there's about 156 million live trees greater than 1 inch diameter on the division's forests. Most of our forest has an age structure in a relatively narrow range, between 70 and 120 years old, with relatively little very young and very old forest. And 15.5% of our land is affected by invasive species to the extent that they threaten the successful regeneration of native tree species without intervention. Now, we'll take a closer look at how CFI data can be used to explore forest carbon dynamics, showing how they can help estimate forest ecosystem carbon stocks at different points in time, as well as how and why they're changing over time. We'll work through this example over the next few minutes using this graph. First, we'll look at stored carbon. Our CFI program measures trees in such a way that we can apply different models of estimating carbon, and so for this example, I've used the models and methods used by the U.S. Forest Service's Forest Inventory and Analysis Program, or FIA, so that we can have an apples-to-apples comparison with estimates of forest carbon available from FIA over Massachusetts and the northeastern U.S. Here, we can see that stored carbon is increasing in the forest the division manages. The dashed brown line represents carbon stored in the above and below ground parts of live trees over 5 inches diameter over all DSPR's forests. The units are metric tons of carbon dioxide equivalent per acre, the unit commonly used in the U.S. to measure forest contributions to greenhouse gas emissions mitigation. And the time frame is since 1980. As you can see, with each passing year, these live trees on lands the division manages store more carbon than the year before. Visualizing the net result of a process, as that first line showed, is useful. But even more important is understanding how and why it's changing, which we'll begin to do as we add data to the graph. These components of change that we'll be adding contribute to what we call flux, or carbon sequestration. We'll start by adding a new y-axis for these new data, showing the change in carbon stocks per acre per year. And again, this will apply to all the new data we'll add. This is one area where the real power of CFI shines. Repeated measurements on the same systematically selected points on the land and trees over time yield valuable insights. And here, represented by the height of this bright green area, we're looking at the growth on existing live trees called survivor growth, the growth on trees that remained alive between any 2 visits to a plot. This is the most substantial component of our forest growth at present. It is positive, adding to our stored carbon each year, and so is above the x-axis in positive territory. And as we can see, the increase in survivor growth is not as rapid as it once was. Now, we've added ingrowth as this light green area, the height of which represents new trees, or young growth in the forest, and are trees that grew into our sample plots between 2 visits. This is, again, an addition to stored carbon, and so is shown above the x-axis. These are smaller trees, and so while it's still adding to overall growth, we wouldn't expect it to be as much as survivor growth. However, it has been declining over the past 20 years and is 50% of what it was during the middle part of the 20th century. As stands and forests develop and disturbance patterns change, there's been less establishment, regeneration, and growth of young and small trees. We call the sum of survivor growth and ingrowth gross growth. Next, we'll add natural mortality. This includes, for this example, the carbon that was in trees in plots that died between two measurements. Since this removes carbon from the live tree pool, it's below the x-axis. As you can see, natural mortality has been increasing in our forests. Factors that can be causing this include stressors such as forest pests, or droughts, or disturbances like severe weather, and also the legacy of landscape-scale patterns of agricultural abandonment, succession, and changes in age structure. The effects of natural disturbances are compounded when trees' crowds are crowded, as they have become over large portions of our land base, and trees don't have the room they need to remain vigorous and resilient. Now, to be clear, these aren't immediate emissions back to the atmosphere. Carbon in standing and down-dead trees can persist for quite some time and is important for myriad reasons, and we remeasure standing and down-dead trees and measure forest floor attributes in our CFI program. But right now, for the sake of this simplified example, we're focusing on additions to and removals from the live tree pool as we focus on growing living trees. Presently, for each ton of carbon per year sequestered in live trees as survivor and ingrowth, about 44% is lost each year as natural mortality. It's very important to account for that mortality in accounting for forest carbon dynamics. Mortality can act, as it does here, as a heavy tax on growth. Simply remeasuring trees that stayed alive during a measurement interval paints an incomplete picture of growth and forest dynamics. In a more complex example, with more time, we could explore the dynamics of standing and down-dead wood, the forest floor, the soils, and other pools. But for now, we're focusing on changes to the live tree pool as the most dynamic, readily influenced by disturbance or humans, and having the largest immediate effects on other ecosystem services. In the study of forest growth and yield, we call survivor growth plus ingrowth minus mortality net growth. Now this is interesting. We can see that while total stocks are increasing, net growth, the rate of carbon sequestration in this live tree pool due to tree growth and death, is declining. Again, carbon in our forests is increasing, but at a decreasing rate. Net growth has declined by 15% over the past 20 years, and by about 37% since the first remeasurement data from our CFI program. Now, we've just added to the graph the carbon in live trees removed by harvesting, the last major component of change. This is a removal of carbon from live tree stocks, so it's below the x-axis again. Harvest removals increased a little from 1980 to the turn of the century, then have declined a bit. We do use standard models to estimate how much carbon is stored in wood products created by trees harvested from our lands, but for the purposes of this simplified example now, we're not showing it. Natural mortality is currently 6.2 times greater than harvest removals. Again, natural mortality is responsible for greater losses of live tree carbon from our forests than forest management. And at present, harvest removals are only about 12.6% of net growth. Having harvest removals well below net growth, in and of itself, is not necessarily sustainable or good for forest health. In fact, having too high a ratio of net growth to removals can lead to excessive stand density and reduced tree health, high rates of mortality, fuels buildup, or other negative outcomes. Net growth minus harvest removals equals net change, and we can see that trends in net change are influenced far more heavily right now by declines in survivor growth and increased natural mortality than by ingrowth or harvest removals. The end result of all these factors, the structure of our forest, inertia, stressors, and management patterns, is that over the coming years and decades, The forests the division manages will likely continue to store an increasing amount of total tree carbon, but if none of those factors changes substantially, the rate at which it is sequestering carbon in live trees, that rate of increase in stocks in that pool, will continue to gradually decrease. We just worked through a quick and straightforward example of how the CFI data are used to estimate forest ecosystem carbon stocks and dynamics over time. I hope this shows how the net change in live tree carbon stocks only tells a small part of the story of forest carbon dynamics. Understanding how and why they're changing is as, if not more, important than that net result. The CFI program provides the measurements and data to help us strive to understand that. It might have seemed easy to arrive at numbers representing carbon stocks and their components of change over time. While climate change and reducing atmospheric carbon concentrations are some of the most pressing issues of our time, those simple numbers representing carbon might make it easy, perhaps too easy, to start thinking about carbon first when we think about forests. While we're able to measure, estimate, and model carbon, it's not easy to do all that, and it takes time and resources. And relying on forests for a single attribute or ecosystem service above others, like wood or revenue, or in this case carbon, does forests a disservice. Forests are far more complex, and forests provide a suite of services, habitat, clean water, wood, and even a sense of place that, maximizing short-term ecosystem carbon gains, may have poor outcomes down the road. One of the key considerations about looking to forests to mitigate climate change we're learning about is stability, helping to ensure stability of high rates of sequestration and stability of stocks in ecosystems and harvested wood products. This means forests need to be resilient in the face of climate change. Forest resiliency is the capacity of a forest to respond to disturbance by resisting damage and stress and recovering quickly while accommodating some change if needed. If it was so easy to arrive at a single number for carbon, though, why should we look any further? Is it even worth trying to think about metrics that we can measure and use as proxies for or components of resilience? And what happens to forest carbon when we manage for resiliency? Fortunately, there's an abundance of work in this emerging field, grappling with these questions and trying to use measurements and data to answer them and continually improve management approaches. The foresters in our program work with affiliates of the Northern Institute of Applied Climate Science, called NIACS, and stay up to date on research into the field of how forests can adapt to climate change. A number of proxies for resiliency have been suggested. They include things like species diversity, projected suitability of those species under climate change projections, tree health, presence of stressors, tree density, and many others at multiple scales. It turns out that foresters had been measuring and managing for some of these in our complex southern New England forests in an indirect way long before resiliency was in our vocabulary. We have so many to choose from and explore, but I'd like to pick one that's straightforward to work through in the time we have. Let's take a close look at structural diversity in tree sizes. Tree size should be a fairly relatable metric. We can save all the explanations of slightly more complex topics like canopy strata, stand structural stages or stage class, or density and resource availability for another presentation. We can turn to these publications to try to understand why a range of tree sizes that are vigorously growing might help forests rebound from stress and disturbance more quickly. Some of those disturbance agents could disproportionately affect a single size class or range of sizes. Having a range of sizes of trees growing vigorously can not only help stands and forests handle a wide variety of future situations that climate change may exacerbate, but also could be beneficial for wildlife habitat and other ecosystem services. Let's explore what the data from the CFI program show. We'll first look at how trees of different sizes are growing. This graph depicts net growth on live trees by 2-inch diameter classes. Here, we're looking at that growth in areas where there has not been a history of management. I'd like to pause here and recognize that I'm presenting current results across these categories of land that has not had some kind of management activity involving the removal of trees, and land that has over the past 60 years, but I'm not entirely comfortable with this strong dichotomy for reasons I'll explain later. Now, roughly speaking, over the 60-year span of our CFI data, approximately 38,000 acres have received some kind of silvicultural treatment. That's approximately 15% of the nearly 325,000 acres currently stewarded by the division. In the areas that DCR has managed, the reasoned, deliberate, and careful application of silviculture and balancing removals with retention appears to help both ingrowth, growing the smallest trees faster, and larger trees are growing faster. Trees in the 16 to 22 inch dBH classes are growing 1.8 times as fast, and trees in the 24 through 36 inch classes grow 1.4 times as fast. It's only in the very largest size classes where we see negative net growth on managed lands. One explanation of this is the trees that we've deliberately retained to live and die in place and become biological legacies. Here, we're shifting from growth on different tree size classes to stocks per acre, carbon density by those same size classes. This represents how much carbon is currently in trees of different sizes, integrating the results of management decisions, disturbances, and stressors over the past 60 years. Where DCR has applied forest management practices and deliberate silvicultural treatments, these are the results. Treatments are tailored to each site, but we typically remove some trees that are less vigorous and usually smaller, and balance removing and retaining larger trees. The net result is that we have greater carbon density in most classes of larger trees on that subset of lands that have been managed. These results are consistent with both traditional silviculture and recent developments in trying to understand forest resiliency. These also have interesting implications for accelerating the development of late successional characteristics, where we try to grow big trees faster and achieve complex structural arrangements. We've looked at growth on different tree size classes. Now let's look at stocks. In terms of structure, for example, the numbers of trees by diameter class, we don't see tremendous differences between managed and unmanaged lands using metrics associated with information theory, like the Simpson's or Shannon's indices, when comparing within a specific forest or even ecoregion. But in general, we see about 10% more carbon in the 16 to 22 inch diameter trees in managed areas, which contain about 37.6% of all live tree carbon, about 22% more carbon in 24 to 36 inch diameter trees in managed areas, which is about 10.3% of all live tree carbon, and 79% more carbon in 36 inch diameter trees and larger in unmanaged areas, which is about 0.8% of all tree carbon. From the last graph of stocks by diameter class in live trees, we notice that it appears that managed lands have less live tree carbon density, and this does illustrate a trade-off. By removing less vigorous smaller trees competing for growing resources, we're allowing the bigger ones to grow faster, and so may have slightly less carbon stocks overall in managed lands. Other components of resiliency shown on this graph include standing and down dead trees. Now, overall, we can see that the difference in carbon density between areas that have been managed and that haven't isn't as large as what we might expect after 60 years. Managed lands have 6.6% less carbon in the above-ground parts of live trees and 13% less carbon in the smaller standing dead tree pool, while managed lands have 33% more carbon in down dead trees. But when we add back the carbon that is still stored in harvested wood products produced with some of the most robust ecological and social protections in the world from the above-ground portions of live trees, we can see that, over a long time period and across Massachusetts on DCR lands, there's really little difference at all in carbon stocks. I'd like to reinforce these ideas further by illustrating that not all forest land performs the same, when it comes to net growth and sequestration in live trees. With a pie chart in the center of this slide, I'm showing the proportion of the division's forest land in different classes of net growth, or sequestration rates, in live trees. What we see here is that, statewide, about 15% of the division's forested land has negative net growth. In other words, in those areas, carbon is leaving the live tree pool faster than it's entering. And, as illustrated in the earlier series of carbon slides, net growth has declined over the past 55 years by nearly a quarter ton of carbon per acre per year. On the low-performing end of this spectrum, we might have stands with widespread mortality events, or tracts in a state of transition, where larger trees are dying and the growth of residual live trees aren't enough to offset that loss. On the high-performing end of the spectrum, we might have stands comprised mostly of younger pole-sized trees, vigorously growing in a race toward the sky. Or perhaps older stands with a complex mixture of trees of different ages, size, and species, all photosynthesizing at different light levels, with complex canopy structures and arrangements, using all the available growing space to the greatest extent possible. If we look at the proportion of land by sequestration class by management status, we see less land in the classes with lowest current sequestration rates and more land with greater sequestration rates in live trees. The proportion of land sequestering carbon at a rate greater than 1 ton of carbon per acre per year in areas with a history of management is nearly double that of areas without management. Again, our foresters are working toward stability of both high rates of sequestration and carbon stocks. And this gets at a core element of what my colleagues who are licensed professional foresters are working toward, identifying areas at poor risk of outcomes, including low rates of sequestration, evaluating alternative courses of action, and deciding on a program of management to try to provide a better outcome over the long term. In some cases, no treatment is the best treatment, but it may not be the best course of action in all cases, especially from a carbon perspective. In this case, the outcome is carbon, but it could be habitat or one of any other ecosystem services. So, as I start to wrap up here, I want to reinforce first that CFI is an important tool to help understand what's happening on the forest land the division stewards, and learn about how and why it's changing and plan for the future. And the data are used to learn how to better apply management practices to our forests. These data seem to show that working over the long term to identify, assess, and improve metrics of resiliency at the stand and landscape scale can provide long-term benefits as well in the form of high, stable rates of carbon sequestration and storage. Before I close, I want to point out that I mentioned earlier that I don't particularly like the strong dichotomy of the presentation of data between managed and unmanaged CFI plots, because the question of management versus no management is never that simple. Management versus no management does not equate to harvest versus do not harvest. Our foresters and program evaluate each site in the context of its own ecosystem and surrounding landscape, and carefully consider the site's adaptive capacity and vulnerabilities. In many cases, there may not be a need to apply any silvicultural tools. In other cases, invasive species control may be warranted, or other treatments on a broad spectrum of opportunity. There's also a tremendous amount of variability from site to site. The way these data are presented provide an aggregate view across all the land stewarded by the division. But recommendations for increasing resiliency are very site-specific. Recommendations for one site or ecosystem, like a northern hardwood stand in the Berkshires, may not be appropriate for another, like a pitch pine scrub oak community in the southeast. These treatments and practices are always integrated into a series of actions that address a potential problem from many different angles. This nuance around each site and the division's goals and objectives is where compromise lies. It's not presented like this to necessarily assert that management is better in any way. We need a variety of approaches, allowing natural processes to unfold in some areas while helping others adapt with the tools we have. It's also important to present information on forest carbon, done here at a very high level, in the context of addressing what we're learning about our forest resiliency and adaptive capacity. Our climate is now changing faster than our forests have ever experienced, and helping it adapt to the urgent change that's occurring, while still providing the benefits on which we rely, is a central challenge, and CFI is one of the tools we can use to learn how to strike that balance. And with that, I'd like to thank you again for your time and opportunity to speak with you this evening. Please let me know if you have any questions, and I'm always happy to meet in the field to take a closer look at specific sites or to continue this dialogue. Thank you.